Beneath the calm surface of the earth, under the cities we build, the mountains we climb, and the oceans we sail across, a silent process has always been at work. It is ancient, relentless, and largely invisible. The slow, grinding movement of the Earth's crust, the shifting of massive tectonic plates, has shaped the world for billions of years. Mountains have risen. Oceans have formed. Continents have broken apart and drifted like puzzle pieces on a molten sea. This geologic rhythm is as old as time itself, and for much of our history, humanity has existed unaware of the forces that churn below. But now, as instruments grow more sensitive and data flows faster than ever before, scientists are beginning to detect something that can't be easily dismissed. A pattern. A shift. A quiet but growing signal that the Earth's outer shell is behaving differently than it once did. In recent years, researchers stationed across a network of seismic observatories have reported subtle but consistent changes in how the crust is responding to pressure. These are not the sensational, headline-grabbing earthquakes that devastate cities or spark tsunamis. These are smaller, more frequent, almost ghost-like quivers, too gentle to be felt, but powerful enough to register in the sensitive readings of high-precision instruments. At first, these tremors were chalked up to random fluctuations, the kind that occasionally ripple through the crust without any deeper meaning. But now, those same anomalies are occurring more often, in more places, and without the expected patterns that usually accompany natural tectonic movements. At global monitoring centers, the data streams in day and night. Scientists scan graphs, track anomalies, and compare current activity to historical averages. And the numbers are becoming harder to ignore. Areas once considered geologically quiet are now showing signs of microseismic activity. Crustal deformation, a slow bending and warping of the Earth's surface, is being measured at rates faster than expected. Subtle uplifts are occurring in regions far from any active fault lines. And in some places, like the western coasts of North and South America, the ground is rising by fractions of an inch per year in ways that don't line up with conventional tectonic explanations. These findings, while not catastrophic in isolation, are causing growing unease within the geoscience community. Not because they point to a single dramatic event, but because they suggest a deeper instability may be taking root across the entire crust. Behind the scenes, conversations among geologists, seismologists, and planetary scientists are shifting in tone. In internal briefings, research papers, and closed-door scientific conferences, a common theme is emerging: the Earth's crust might be entering a period of heightened volatility. Teams that were once focused on localized fault zones or volcanic systems are now taking a step back to look at global correlations, asking whether what we're witnessing is a widespread geological awakening, a transition in the crust's behavior that could affect everything from natural disaster patterns to the structure of our continents themselves. And while many are careful not to speculate publicly, the urgency in their private work is unmistakable. This isn't just academic curiosity. These findings have begun to influence real-world decisions. Government agencies are quietly funding expanded geological surveys. Emergency preparedness drills are increasing in areas that haven't seen major seismic activity in decades. Insurance firms are reevaluating their risk assessments for entire regions based on new crustal stress models. Even in the construction industry, some engineers are being asked to update structural safety standards, not because of a major quake, but because the crust beneath our feet seems less stable than it was 10, 20, or 30 years ago. Something is shifting, and the people who measure and model these forces for a living are no longer entirely comfortable with what they're seeing. And while the average person goes about their day unaware, the Earth continues to move. Unseen. Unfelt. But not unnoticed. Not anymore. Because today, we stand at the edge of an unknown chapter in the story of our planet. One where the signs are subtle, the signals complex, and the conclusions still forming. Scientists are not sounding the alarm just yet, but their growing unease suggests that something is happening deep beneath the surface that we may not fully understand. Not yet. But it's becoming harder and harder to ignore. Now, before we continue, we would like to encourage you to consider liking the video and subscribing. As scientists continue to sift through the mounting data and piece together the intricate puzzle of crustal behavior, one potential cause has quietly begun to rise above the rest. It's not something visible on the surface. There are no obvious signs in the sky or on the land. But deep beneath the crust, far below the ground we stand on and even deeper than the layers accessed by our deepest boreholes, lies a realm of enormous heat, pressure, and fluid motion. This vast interior layer, known as the mantle, plays a critical, often underestimated role in shaping the very foundation of our planet's surface. For decades, geologists have understood that mantle convection, the slow, churning motion of semi-solid rock within this deep zone, drives the movement of tectonic plates. But now, increasingly precise observations suggest that something may be changing in that engine room beneath our world. And if that change is real, it could be triggering a cascading effect that's causing the Earth's crust to grow more unstable than ever before. To grasp the importance of this potential shift, it's helpful to imagine the Earth as a layered system, much like a peach, though far more complex. The crust, which we live on, is a thin, brittle outer skin. Beneath it lies the mantle, a vast region of superheated rock that behaves like a thick, slow-moving fluid over geological time. This is where the story begins. For millions of years, thermal energy rising from the planet's molten core has created convection currents in the mantle, upwellings of hotter material and downwellings of cooler rock. These currents are not chaotic or random. They follow long-established patterns, subtly guiding the continents and ocean floors above like giant conveyor belts. These mantle motions push and pull on tectonic plates, causing them to drift, collide, or slide past one another. It is this process, as slow and silent as it may be, that causes earthquakes, fuels volcanic eruptions, and forms mountain ranges. But in recent years, new satellite imaging, deep Earth tomography scans, and geodetic measurements have painted a troubling picture, one that suggests these convection currents may be altering in strength, shape, and direction. What was once a relatively balanced system, with long, stable flow patterns, might now be undergoing a period of reorganization. The implications of this are profound. A change in mantle flow would inevitably place new stresses on the crust above it. Areas that were once geologically calm might begin to experience uplift, as warm plumes push against the underside of the lithosphere. Other regions might see subsidence or compression, as cooler currents sink more aggressively. The cumulative effect of these shifting pressures could destabilize entire tectonic plates, creating the kinds of anomalies now being picked up by seismometers, GPS sensors, and satellite-based elevation maps around the world. In one particularly compelling study published recently, a team of researchers used seismic wave data to model deep mantle dynamics beneath the Pacific Plate. What they found surprised even seasoned geophysicists. Their models indicated that a massive mantle plume, essentially an upwelling of superheated material, had not only intensified in recent decades but had begun to deviate from its historically stable vertical path. Instead of rising straight upward, this plume appeared to be leaning laterally, pressing unevenly against the crust. Such a directional shift would alter stress loads across vast swaths of the Pacific Basin, potentially explaining why once quiet coastal regions like Oregon, Japan's eastern seaboard, and parts of Chile have begun to experience unusual seismic and geodetic readings. These aren't just isolated quirks. They might be symptoms of a much larger internal rearrangement, a subtle rebalancing act that's placing new and unfamiliar strains on the Earth's outer shell. It's important to remember that these changes are not happening overnight. Mantle convection is a slow and deliberate process, operating on timescales that can span thousands, sometimes millions, of years. But the recent uptick in data resolution, combined with an expanding global network of seismic stations and remote sensing satellites, has allowed scientists to detect even the faintest signals of change. When viewed in isolation, a small uplift in ground level or a microtremor might seem meaningless. But when thousands of these data points begin to cluster along emerging fault zones or align with deep mantle anomalies, a pattern begins to take shape, one that can no longer be ignored. More intriguingly, some of the current crustal deformations are happening in regions that have historically been regarded as tectonically stable. Portions of the African continent, for example, long considered among the most geologically quiet places on Earth, have shown signs of subtle deformation in recent satellite radar imagery. In parts of Central Australia, researchers have noted inexplicable strain accumulation in bedrock that hasn't shifted significantly in hundreds of millions of years. While these deformations are still minor in terms of absolute movement, often measured in millimeters, they're appearing in locations where no significant surface drivers exist. The most plausible explanation? A new pattern of deep mantle stress redistribution, reaching upward through the lithosphere and ever so gently distorting the crust above. And so the question arises, why now? What could be causing this change in the mantle's behavior? Some theories point to a natural cycle, an inevitable phase in Earth's long thermal evolution. Others suggest a connection to surface processes, like glacial melting and oceanic mass redistribution, altering the balance of weight on the crust and thus influencing mantle flow beneath. There's even growing speculation that core-mantle boundary interactions, once considered largely static, might be more dynamic than previously thought, with subtle shifts in core heat output sparking mantle convection realignments. While consensus remains elusive, one thing is becoming increasingly clear. The forces that once drove plate tectonics with relative predictability may now be entering a period of transition, and that transition could be laying the groundwork for more widespread crustal instability. Even within the scientific community, the language used to describe these events has begun to shift. Where once terms like stable, consistent, and predictable were common descriptors of mantle convection patterns, we now see words like erratic, nonlinear, and asynchronous creeping into research papers. It's a subtle but telling change, a linguistic reflection of mounting uncertainty. Because if mantle convection is indeed shifting in ways that scientists don't fully understand, then the crust it supports is no longer on solid ground, metaphorically or literally. As we continue this exploration into the unsettling signals coming from beneath our feet, it's worth remembering that the Earth, for all its familiarity, remains a planet in motion, a dynamic, living system shaped by forces that extend far beyond our reach and comprehension. The mantle, though hidden from view, may very well be the silent conductor of a new and more chaotic geological symphony, one whose opening notes we are only just beginning to hear. Beneath our everyday awareness, beneath even the reach of our most advanced drilling equipment, the Earth churns with an ancient rhythm. That rhythm, slow, powerful, and nearly imperceptible on the surface, is the motion of the mantle. And while this motion has long been considered a foundational constant of our planet's geodynamics, mounting evidence now suggests it may not be as stable or uniform as once believed. The idea that mantle convection could be subtly shifting its patterns might seem abstract, even distant. Yet the implications are astonishingly close to home. These currents, far from being irrelevant geological trivia, shape the rise and fall of continents, the spread of oceans, and the explosive power of earthquakes and volcanoes. If the driving force of this process is beginning to alter, even slightly, the cascading effects could eventually ripple across the globe, reshaping coastlines, destabilizing fault zones, and challenging centuries-old assumptions about tectonic behavior. Consider, for a moment, how dependent we are on the relative predictability of Earth's internal processes. Entire cities are built on historical geological stability, regions considered safe due to their distance from known fault lines or past volcanic activity. Infrastructure is planned according to risk assessments based on past seismic activity. Insurance industries, national disaster agencies, and even international diplomacy have all, to some degree, relied on the assumption that Earth's internal mechanisms remain steady and that major changes occur only across vast timescales. But mantle convection is not a machine. It does not obey the rigid constancy of a factory's gears. It is a living, flowing system of heat and rock, influenced by countless variables we still only partially understand. If its flow patterns are changing now, at this very moment, then so too is the entire framework upon which our surface world is built. What's particularly compelling, and deeply unsettling, is how many of these convection anomalies are interconnected. In the past, a shift in one region, say, under the Indian Ocean, might have been viewed as an isolated case, a localized fluctuation of thermal activity. But new global models are revealing something different. Areas of mantle upwelling or downwelling are beginning to interact in ways that suggest a global realignment may be underway. Think of it like a series of gears beneath the crust. When one gear begins to shift, the others must adjust in kind. Plumes that were once vertical may be pulled sideways by changing thermal gradients. Slabs of cooled lithosphere that once sank steadily into the deep mantle may now be stalling or deviating, creating a kind of geological traffic jam beneath subduction zones. These interactions, though buried deep, have real consequences on the surface, manifesting as stress accumulations, slow ground uplift, or even the quiet stretching and cracking of continental interiors that were once thought immovable. Advanced imaging techniques like seismic tomography have become invaluable in this exploration. Much like a CT scan for the Earth, this method allows scientists to peer into the mantle by analyzing the way seismic waves travel through it. What these scans are revealing is both fascinating and worrisome. In several major regions, including the Western Pacific, Central Africa, and parts of Antarctica, there are signs of temperature anomalies in the mantle that don't align with existing models. Hotter zones are appearing in places that traditionally haven't exhibited much thermal activity, and cooler regions are expanding in ways that may be disrupting the flow of surrounding material. These temperature differences matter. Even small changes in mantle temperature can alter the viscosity of rock, which in turn affects how easily convection currents can move. A slight increase in viscosity could effectively clog a convection path, diverting flow elsewhere, adding strain to plate boundaries and potentially contributing to the slow fragmentation of stable crustal blocks. And then there's the question of rate. While mantle motion is infamously slow, typically measured in centimeters per year, scientists are now detecting microaccelerations and shifts in flow direction that defy previous expectations. These changes might not be immediately dramatic on the surface, but they represent a deeper truth. The engine of the Earth is not static. It breathes, it pulses, and occasionally it lurches into a new phase of movement. One recent study noted that the mantle beneath the Pacific Northwest had experienced a subtle but consistent tilt over the past 2 decades, barely perceptible by human standards, but enough to nudge the surrounding crust and potentially contribute to a rise in microseismic activity observed in the region. It's not an earthquake. It's not a volcano. It's something quieter, stranger, and in many ways more haunting, a deep structural shift that may only show its true consequences in decades or centuries to come. What's perhaps most perplexing is the absence of a clear trigger. In other natural systems, change is often tied to a catalyst, an external force, a sudden event, a cause and effect chain that can be followed. But the changes being detected in mantle convection are happening in a kind of geological silence. No asteroid impact, no planetary alignment, no solar phenomenon has been identified to explain why the convection system might be transitioning. This silence has led some researchers to speculate that we may be entering a natural but poorly understood phase in the Earth's internal cycle, perhaps one that recurs every few 100,000 years, one that has eluded detection until now due to the limitations of ancient records and modern instruments. If true, we are witnessing a phenomenon that has occurred before, but never under the scrutiny of human technology, and never with billions of lives and global infrastructure hanging in the balance. Yet despite the mounting evidence, many questions remain. Are these shifts temporary fluctuations, or the beginning of a long-term transition? Will the changing convection patterns stabilize in new configurations, or will they remain chaotic and unpredictable? And perhaps most critically, can we forecast where the next signs of crustal instability will emerge, based on the evolving flows below? Scientists are racing to answer these questions, poring over petabytes of seismic data, developing next-generation mantle flow models, and collaborating across disciplines in a way rarely seen before. There's a growing sense of urgency, not panic, but a sober recognition that something fundamental may be changing, and we are only beginning to grasp its magnitude. The reality is, we are living in a rare moment in geological history, a moment when deep Earth processes may be shifting in real time, and humanity, for the first time, has the tools to observe it happening. But observation is not the same as control. As we stare deeper into the churning heart of our planet, we are reminded that Earth's inner workings remain humblingly complex and beyond manipulation. We can measure, we can model, but we cannot stop the mantle from flowing where it will, nor predict with certainty the path its changes will carve into the crust above. And so, as the silent motions continue beneath us, their whispers growing ever louder in our instruments, we are left to wait, to study, and to wonder, how much longer can the surface remain stable while the deep earth reconfigures its ancient rhythm? How close are we to witnessing the first outward signs of a truly global geological shift, one born not from catastrophe, but from the slow and steady heartbeat of the mantle itself? While the ever-churning mantle remains one of the most enigmatic engines of change deep within the earth, it is by no means the only force influencing the shifting crust above. As we ascend from the molten flow of the mantle to the rigid, fractured shell that forms our planet's outermost layer, a different kind of story begins to emerge, a story not about slow, ancient convection currents, but about the relentless rebound of the Earth itself. This process, known as post-glacial rebound or isostatic adjustment, may sound like a quiet, passive geological response to a long-finished ice age. But in reality, it is a dynamic and ongoing reshaping of the Earth's surface, one that is gathering momentum in unexpected ways and raising critical concerns among geologists worldwide. To understand this phenomenon, we must journey back tens of thousands of years to the heart of the last ice age. During this period, vast expanses of the northern hemisphere were blanketed in colossal glaciers, miles thick in some places, their immense weight pressing down on the Earth's crust like a colossal, frozen hand. Beneath these glaciers, the crust sagged, deforming under the sheer mass of the ice above. It wasn't just a surface depression either. This pressure displaced material in the mantle below, pushing it outward like a squeezed sponge. For thousands of years, the Earth held its breath beneath this burden. But the ice age ended. The glaciers began to melt, retreating slowly at first, then more rapidly as the climate warmed. As this icy weight lifted, the land began a long, slow rebound. It's tempting to imagine that this rebound is merely a gentle, upward motion, like a sponge returning to its shape. But the Earth is not a sponge. Its crust is not soft or uniform. The mantle beneath is not a liquid that flows freely. Instead, this process has set off a complex and often uneven response across vast regions. Some areas are rising faster than others. Some are shifting sideways. Faults that have been locked and silent for centuries are waking up. Ancient stresses are being reactivated. In some cases, entirely new stress patterns are emerging. What makes this particularly important now, thousands of years after the ice began to vanish, is that the rate of rebound is accelerating. Recent satellite measurements using GPS and gravimetric data show that parts of Canada, Scandinavia, and Siberia are rising at rates exceeding 10 millimeters per year. That might sound small, but in geological terms, it's astonishing. And it's not just about vertical movement. The crust is warping, twisting, and redistributing stress in ways we're only beginning to quantify. Beneath the Arctic Ocean, for example, researchers have detected deep crustal faults undergoing reactivation, shifting ever so slightly as the rebounding land alters the regional stress field. These are not areas traditionally associated with seismic activity, but they are becoming more active. Even more fascinating, and troubling, is the interplay between this rebound and seismic hazards in regions previously considered stable. Take Finland, a country not typically thought of as earthquake-prone. Yet in recent decades, the region has experienced a noticeable uptick in seismic events, many of them shallow and unusual in character. Seismologists have traced these events to isostatic rebound, specifically, the way in which the Earth's crust is adjusting to the removal of ice, triggering movement along ancient faults that had lain dormant for millennia. These are not random quakes. They are echoes of a deep, glacial history colliding with a rapidly warming present. And that's just one layer of the issue. As the Earth rebounds, it doesn't do so in a vacuum. The redistribution of mass on the planet's surface, whether from melting glaciers, shifting groundwater, or receding polar ice, has implications for the balance of the entire lithosphere. Subtle changes in gravitational forces, crustal loading, and even rotational wobble can cascade into larger tectonic shifts. This means that rebound in one region might influence fault lines thousands of miles away. One study out of Norway proposed that rising land in Scandinavia might be subtly altering stress on mid-Atlantic ridge zones. It's a domino effect, but one in slow motion, unfolding beneath our feet, hidden behind the illusion of surface calm. And then there is the water. As glaciers melt, they don't just free land to rise. They also pour trillions of gallons of fresh water into the oceans. This influx changes sea levels, but more importantly for this discussion, it redistributes mass across the globe. The added weight of ocean water along coastal margins can press down on the crust, creating flexure zones, areas where the land buckles, sags, or strains under the load. Coastal cities, once thought to be safe from tectonic risks, may now find themselves subject to new forms of stress. It's not tectonic plate movement in the traditional sense, it's crustal deformation born from imbalance. And this imbalance is becoming more pronounced with every passing year. Climate change, which is accelerating glacial melt at unprecedented rates, has effectively poured fuel on the fire of post-glacial rebound. What should have been a slow, natural process spanning tens of thousands of years is now unfolding on a much shorter timeline. The Earth, which prefers to move at a glacial pace, is being forced to adjust more quickly, and the results are far from uniform. Some regions are rising too fast for ecosystems to keep up. Others are sinking. And the stress map of the crust, once relatively stable, is beginning to look like a chaotic web of pressure points and fault awakenings. All of this points to one unsettling reality. The Earth is still responding to the end of the last ice age, and it's doing so in a world that is heating rapidly, changing faster than it can adapt. As land rises in some places and sinks in others, as old faults awaken and new ones form, scientists are increasingly aware that post-glacial rebound is not a historical footnote, it's a current, an accelerating force, reshaping the crust in ways both subtle and dramatic. And while much of the focus in tectonic science has historically centered on the big players, the plate boundaries, the subduction zones, the rift valleys, it is now becoming clear that some of the most significant crustal shifts may emerge not from direct plate collisions, but from the long echo of ancient ice, reverberating through time and manifesting in seismic and structural changes around the globe. It's not just a matter of where the plates are moving, but how the Earth is rebalancing its own shape in response to the burdens it once bore, and the new ones it now faces. To appreciate the full magnitude of what post-glacial rebound truly entails, we must go beyond the simplistic idea of land slowly rising after ice melts. It's not just a passive lifting of the Earth's skin, it's a comprehensive geodynamic reaction, a kind of planetary exhalation after millennia of glacial suffocation. This process touches every layer of the Earth's geophysical system, from the delicate crust to the sluggish, creeping mantle below, and even extending into atmospheric and oceanic interactions. The Earth is not simply bouncing back, it is readjusting itself in a deeply interconnected and sometimes unpredictable manner, often with surprising consequences. This rebound is a viscoelastic process, meaning that the Earth responds both elastically and viscously to the changes in pressure. The elastic part happens relatively quickly, crustal uplift, minor shifts, but the viscous component is much slower and more complex. Picture the mantle as an incredibly thick, slow-moving fluid. When the glaciers melted, the displaced mantle material didn't immediately flow back to its original position. It began to do so gradually, like molasses crawling back toward an empty indentation. But here's where it gets particularly interesting. As this material shifts, it doesn't just affect the site of the rebound, it alters pressure and stress distribution across vast regions. The Earth is interconnected on scales we still don't fully comprehend. One of the more unexpected consequences of post-glacial rebound is the reactivation of intraplate faults, faults not located near plate boundaries. These are often ancient, sometimes billions of years old, remnants of former tectonic collisions, rifts, or shear zones long thought dormant. However, the gradual reconfiguration of stress due to isostatic adjustment is now awakening many of these old structures. Geologists and seismologists have begun to notice patterns of minor, shallow earthquakes along these forgotten fault lines, especially in high-latitude regions that were once deeply buried beneath thick ice sheets. In Canada's Hudson Bay region, for instance, instruments have detected ground motion consistent with vertical uplift, and more notably, localized seismic activity. The Canadian Shield, one of the most ancient and stable continental cores on the planet, is now witnessing subtle but measurable seismic shifts. This isn't coincidental. The rebound is slowly stretching and pulling at these old rock formations, reintroducing movement where none had existed for tens of thousands of years. It's as if the Earth's ancient scars are beginning to throb again, not from direct trauma, but from the slow return of pressure equilibrium. And this isn't merely a geological curiosity. Intraplate seismicity, especially in regions not traditionally prone to earthquakes, can catch local infrastructure and populations completely off guard. Cities and towns built without seismic precautions may find themselves more vulnerable than those in well-known tectonic zones. This vulnerability compounds the growing concern among scientists that post-glacial rebound isn't just a geological background process. It's an emerging seismic hazard, one that is both under-discussed and poorly understood in mainstream discourse. Adding yet another layer to this dynamic is the feedback loop between climate and tectonics. As the Earth warms and more ice melts, not just in the polar regions, but from mountain glaciers across the globe, the rate of mass redistribution intensifies. The oceans swell. Coastal weight increases. The vertical loading and unloading of Earth's crust becomes more complex and more chaotic. These changes are not happening in a vacuum. Every ton of water moved from ice to ocean subtly shifts the stress map of the planet, bending the crust and altering its internal tensions. And because Earth's crust is not uniform, because it is fractured, segmented, and varied in thickness and composition, these stresses do not distribute evenly. Some areas absorb the changes gracefully. Others, particularly those with pre-existing weaknesses or ancient fault lines, respond with strain, buckling, and eventually, release. It's important to understand, too, that this process doesn't happen in isolation. Other Earth systems begin to interact with this shifting crust in unexpected ways. As the crust rises in one region, groundwater tables shift. Rivers change course. Subsurface aquifers are squeezed or expanded, altering pressures underground that can influence everything from volcanic activity to sinkhole formation. For instance, in areas like Iceland, which are simultaneously experiencing rebound and active volcanism, the combination of mantle plume activity and isostatic adjustment may be accelerating changes beneath the surface. The uplift isn't merely bringing land higher, it may be triggering deeper activity, potentially priming the system for future eruptions. Furthermore, scientists are beginning to examine the possibility that earthquakes triggered by post-glacial rebound may be more energetic than expected. While many are small and go unnoticed by the public, some show unusual characteristics. Their focal mechanisms, the direction and type of fault movement, sometimes don't align with conventional tectonic patterns. In other words, these are not typical quakes caused by plates grinding past each other. They are often vertical, reverse fault events caused by the crust being lifted from below, rather than compressed or sheared laterally. This raises questions about how well our current models of seismic risk account for this growing source of tectonic pressure. There's also growing concern about critical infrastructure in affected regions. Dams, nuclear power plants, bridges, and underground pipelines, many were constructed with historical seismic data in mind, data that may no longer apply as post-glacial rebound continues to reshape the crust. If old fault lines in Northern Europe, North America, or parts of Asia become active again, will the infrastructure in those areas withstand the unexpected stress? Engineers and geologists are increasingly pushing for updated risk assessments, especially in regions like the Baltic Sea Basin, northern Russia, and the Canadian Arctic, where the ground is still actively rising at measurable rates year after year. Even culturally, the consequences are beginning to emerge. Indigenous communities in northern Canada, Alaska, and parts of Scandinavia have long observed changes in the land, new cracks in the earth, strange shifts in terrain, lakes appearing or disappearing seemingly without warning. These anecdotal observations, passed down through generations, are increasingly being taken seriously by geoscientists as they align with satellite and GPS data showing ongoing vertical and lateral movement of the land. The Earth itself is changing shape beneath these communities, not due to earthquakes or volcanic eruptions, but because it is still releasing the slow, pent-up stress of a lost world of ice. And perhaps the most sobering realization is this: the process is not over. In fact, we may be in the early stages of the rebound's most active period. The full geological response to the melting of the great ice sheets may take tens of thousands of years to fully unfold. What we are witnessing now, rising coastlines, inland seismic tremors, crustal flexure, is only the beginning. As more of the world's remaining ice melts, this process will only intensify. The crust will continue to groan, crack, and rearrange itself in response to both ancient burdens and modern disruptions. In this grand, slow-motion reconfiguration of the planet, post-glacial rebound stands as both a testament to Earth's resilience and a reminder of its sensitivity. It is the Earth's way of resetting the balance, of slowly healing from the weight of its frozen past. But like any healing process, it is not without pain and not without consequence. As scientists continue unraveling the many reasons behind Earth's increasingly unstable crust, a small but growing number of researchers, theorists, and forward-thinking geophysicists are beginning to entertain a possibility that edges into the speculative. It isn't yet a mainstream idea, and it's not taught in geology classrooms or printed in standard textbooks, but it is quietly gaining traction in some circles that dare to ask, what if something deeper, far deeper than we've dared to explore, has begun to stir beneath the Earth's crust? What if the foundations of the planet itself are not as inert, as unchanging, as we have always believed? The theory goes like this: for decades, we've accepted that the Earth's mantle and core are relatively stable systems, governed by slow convection cycles and heat diffusion from the core outward. But recent, puzzling anomalies in gravitational measurements, heat flux readings, and deep seismic data have begun to paint a picture that some interpret as the awakening of a long-dormant planetary phenomenon. Beneath our feet, thousands of kilometers down, within the swirling layers of the outer core, or perhaps even deeper, something may be shifting. Not merely geologically, but structurally. And some theorists have begun referring to this hypothetical event as the core pulse hypothesis. According to this idea, the inner Earth operates on extremely long cyclical rhythms, far beyond the scope of human civilization's record-keeping. We often think of geological time as something slow and relatively consistent, but what if, every few million years, the Earth's core undergoes a kind of internal convulsion? Not a violent explosion, but a slow, powerful pulse of energy or heat, perhaps tied to fluctuations in radioactive decay rates, magnetic field alignments, or even interactions with the gravitational pull of celestial bodies like the moon or sun. These hypothetical pulses could send rippling waves of energy upward through the mantle, disturbing convection patterns, increasing pressure on the crust from below, and destabilizing fault lines that had previously been dormant. At first glance, it may sound like science fiction, and perhaps it is, but this theory is not entirely baseless. Seismologists have recorded mysterious ultra-low velocity zones, ULEZs, at the boundary between the mantle and core, regions where seismic waves suddenly slow down as if passing through a strange, partially molten or anomalously dense material. These zones have baffled researchers for decades. Some believe they may be composed of ancient subducted crust. Others suspect they may be the remnants of massive, ancient impact events. But under the core pulse hypothesis, these zones could represent the Earth's pressure valves, absorbing energy from deep within and distributing it gradually upward, until, one day, the system becomes saturated. And when that saturation point is reached, it may not be a singular event, but a planet-wide reaction. The Earth's lithosphere, the rigid outer shell, could begin to respond to this subtle but rising pressure. Microseisms could grow more frequent. Faults under the ocean floor might begin to slip. Volcanic activity could gradually intensify in unanticipated places, not due to surface subduction or magma chambers, but because of a slow, planet-wide exhalation from the core itself. Supporters of this theory often point to subtle shifts in the Earth's magnetic field as indirect evidence. It's well known that the magnetic field, generated by the churning of molten iron in the outer core, has been weakening in certain regions over the past century. The South Atlantic anomaly, a mysterious zone of reduced magnetic intensity, has puzzled scientists for years, growing in size and strength. Could these fluctuations indicate more than just surface-level magnetic irregularities? Could they, in fact, be the early signs of a core-wide reorganization, a prelude to an event that would radiate upward through the mantle and into the crust? Some researchers even speculate about the possibility of resonance, a phenomenon where external forces such as gravitational alignments of the Moon, Earth, and Sun could trigger or amplify these pulses. While it may sound far-fetched, Earth's own tides and tectonic movements are already known to be influenced by the lunar cycle. If minor gravitational forces can move oceans and cause measurable stress on tectonic plates, what would happen if those same forces aligned perfectly with an unstable or transitioning core? Could the planet itself begin to vibrate, not in a cataclysmic, explosive way, but in subtle waves that ripple upward and outward, testing the stability of the crust? And as wild as it may seem, even ancient mythologies have described the Earth as a living entity, breathing, shifting, and periodically stirring. In many cultures, there are stories of the Earth waking up or reawakening after long periods of slumber. While we must tread cautiously when mixing folklore with science, it is fascinating how such narratives align with the fundamental idea behind the core pulse hypothesis, that the planet may operate on deep, cyclical rhythms that are largely invisible to us, until they are not. Another interesting angle within this theory relates to deep Earth neutrino emissions. Neutrinos are nearly massless particles that pass through matter with almost no interaction, and we've only recently begun detecting those that originate from within the Earth. Some anomalies in neutrino readings from observatories in Japan and Italy have raised eyebrows, showing unexpected fluctuations in output from deep within the mantle. While these variations could be statistical noise or unrelated background interference, others suggest they may be indicative of changing conditions deep below, possibly related to shifting radioactive decay or temperature gradients in the core. Could this be the equivalent of an early heartbeat, a prelude to a much larger movement within the Earth's hidden engine? Importantly, this theory doesn't require a sudden doomsday scenario or Hollywood-style apocalypse. It is far more subtle, and perhaps more unsettling for that reason. The core doesn't need to explode, and the mantle doesn't need to boil. Instead, the idea is that the entire Earth, as a system, is slowly entering a new energetic phase, one marked by rising internal pressures, increasing thermal gradients, and the slow, relentless tension this places upon the crust. Over the coming decades, or perhaps centuries, this could manifest as a noticeable uptick in earthquakes, volcanic eruptions, strange ground uplift, and even new rifts forming in seemingly stable regions. As of now, the core pulse hypothesis remains on the fringe, discussed in speculative papers, late-night geology forums, and theoretical modeling labs. But as our instruments grow more precise and our models more complex, we may begin to see signs that lend it more credibility. And if even part of the theory holds true, then it raises a profoundly humbling question: what if Earth itself is entering a new chapter of internal evolution, one that we can feel, but not yet fully understand? If the crust beneath our feet is indeed becoming more unstable, if the planet itself is subtly shifting into a new and unpredictable phase of geological behavior, then the implications for humanity extend far beyond the tremors and eruptions we might first envision. It's not merely a matter of disaster preparedness or engineering resilience. It is a question that reaches into our collective psyche, into the fabric of who we are as a species and how we see our place on this planet. Because when the ground becomes uncertain, when the very Earth we've always assumed to be solid starts to whisper of change, it forces us to reevaluate everything we thought was permanent. For all our technological advancements, all our space missions and scientific triumphs, we are still deeply tethered to this fragile shell of rock that floats above a churning sea of molten fire. Civilization, our cities, our power grids, our monuments, our histories, is built on a thin crust no thicker in proportion to the planet than the skin of an apple. And if that crust begins to shift, Even subtly, the ripple effects through our societies would be profound. Coastal cities built atop fault lines or volcanic zones could become untenable. Agricultural regions might be disrupted by new fissures, sudden uplift, or changes in underground water flows. Whole ecosystems could be destabilized, not by climate change alone, but by tectonic transformations beneath them. But the deeper implication, the one that lingers longer than the scientific observations or the speculative theories, is the existential one. We have always taken for granted the illusion of permanence. Mountains seem eternal. Continents appear immovable. The horizon feels unchanging. And yet, the geological record tells a different story, of upheaval, submersion, rifting, and transformation. We live in a brief moment of calm between epochs of violent motion. If the Earth is now moving once more, even if slowly, it could mark the beginning of a new chapter, not just in geology, but in human history. There is something quietly humbling about the idea that the Earth, our home, might be evolving in a way that is entirely indifferent to us. We are so accustomed to being the drivers of change, from reshaping coastlines to altering the atmosphere, that we rarely consider the possibility that the planet could change without our influence. That it could wake up, shift, sigh beneath our cities, and carry on, whether we are ready or not. This potential instability doesn't just challenge our engineering, it challenges our worldview. It reminds us that we are not the masters of Earth, but its passengers. For some, this realization might spark fear or helplessness. But for others, it may ignite something more valuable, a deeper reverence. A sense of awe at the living, breathing nature of this planet. A renewed respect for the cycles and forces that have shaped it long before humans ever walked its surface. It might compel us to think more holistically, not just about how to survive potential tectonic upheaval, but about how to live in harmony with a world that is far more dynamic than we've allowed ourselves to believe. It could also force us to confront uncomfortable truths about our current trajectory. If Earth's crust is becoming more volatile, then our dependence on fragile infrastructures, our concentration of populations in tectonically sensitive zones, and our tendency to ignore deep time processes in favor of short-term gains may all come under scrutiny. Perhaps it is time to begin rethinking the architecture of civilization itself, not with panic, but with foresight. Not with fear, but with respect for the slow, rumbling voice of a planet that is never truly still. And yet, there's a strange beauty in it too. Because if Earth is alive in ways we're only just beginning to grasp, if it pulses, breathes, shifts, then so too can we. Humanity has endured ice ages, supervolcanoes, and global floods. We've migrated, rebuilt, adapted, and thrived. If instability becomes the new normal, then perhaps it is not a death knell, but a call to evolve once again. A call to rediscover our resilience. To blend ancient wisdom with modern insight. To live not just on the Earth, but with it. So what does this all mean for us? It means awareness. It means preparation, not just in bunkers or blueprints, but in mindset. It means teaching our children that the ground may not always be still, but that we can still find balance. It means recognizing that change, no matter how vast or unpredictable, does not necessarily spell doom. Sometimes it simply spells transformation. And transformation, if approached wisely, can be a beginning. After all, maybe the Earth isn't destabilizing out of malice or chaos. Maybe it is simply continuing a journey we've yet to fully understand, a journey we were always meant to witness. If you've found yourself drawn into this unfolding mystery, if the subtle tremors of truth and possibility have stirred something within you, then now is the time to stay connected. This is just the beginning of a much deeper journey, one that challenges what we think we know about the ground beneath us, and what lies ahead. So if you haven't already, make sure to subscribe to the channel and tap the notification bell. That way, you won't miss the next chapter in this evolving story.